Okay, introduction. So what do you understand by the word statistics? So we're going to start with statistics. What do you understand by statistics? And what I'd like you to do is to write down what you think statistics is or are. Okay, I'm going to pick on our youngest member, our newest member, Daniel. What do you think?
I've always thought statistics. Anytime I thought statistics, I just thought of it as like a collection of numbers and the information that they.
Chunk of information, numeric.
Yes.
Okay, yeah. Then how about Russ, who's been north of forever on this watch?
I put numerical representation of facts.
Okay. You're also going to add some information. What should it be? Selections of data.
Facts and information compiled to show trends or averages.
Okay. Well, to me, first of all, we can have a statistic. There can be several of them which are statistics. And statistics is also a branch of engineering, science, numerology to measure. So first of all, statistics, the subject, really to me is the analysis of numbers, anything to do with the analysis of numbers. But when we come on to a statistic, just one of them, you can't have one of them. To me, that's a very, very important thing. It's telling me that, let's think of an average. You're all kind of aware of the word average. We're going to lock in exactly what I mean by that. So let's say I've got a whole box of pens. Here we go. And I say, I want to know the average length of the pens. Okay? So we say, let's go measure them. Steve, you're the expert on measuring ones. Yeah. So you could go measure those things. Yeah, you could give the average. That's a statistic. Oh. What's going to happen to your average now? It's going to change. So the statistic has changed. There's some number somewhere which is the actual average length of these pens. And it's called a parameter. And the statistic is our best estimate, based on Steve's high quality measurements, of what that parameter is. So a statistic is from actual numbers, actual data, and it's heading towards these things called parameters. And the parameter is the real average length. There's other parameters as well, but that's just one. And the statistic is our best estimate. So if I gave you one pen and said, what's the average length of a pen? The best you can do is to measure that and say that's the average length. Yeah. And it's going to be some very, you know it's not very accurate. Because I might have, drop the end up, or I might have shoot the end and change its length. Now I give you two, and we can measure two of them. We can find their average. That's now a statistic. It's our next best estimate of this unknown parameter. And as we get more and more, we're going to have more and more confidence, and that's where the uncertainty analysis starts to come in. Statistics, we're back here again. So a statistic to me, yes, it's all connected with the collection of data, the analysis of data, the presentation of data. That's the subject of statistics. But it also has a separate meaning. A statistic is this, our best estimate of a thing we'll find is called a parameter, and that's the things like an average. So there's going to be descriptive. We can have colors and things like that. So it doesn't have to be numerical. Different types of graphs, lots of them. You know, as soon as you bring Excel, how many of you have used Excel? Hopefully all of you. And you click on Insert Graph, and immediately Bill Gates' mechanism pops into life and gives you graphs that are absolute nonsense, some of them. Have you ever used those new three-dimensional things with cones and cubes and things like that? If you use those, you've just produced a scientifically nonsensical graph. And if you use it properly, if it's programmed wrongly, if it was programmed correctly, then it wouldn't present the information you wanted to see anyway. So we might get into some of that as well. And then making decisions on incomplete information and uncertainty analysis. So let's start talking about some definitions of populations. Population. Population is everything. Every pen that's ever been made and ever will be made. That's my population. I can refine it down a little bit. If I got a die being, got two meanings, doesn't it? At least three. Let's get the three maybe. Half of a pair of dice. Yes. Two dice, one die. True? Yeah. So if I have a die, the population of numbers is 6. 1, 2, 3, 4, 5, and 6. Those are the only possible things that can happen if I roll. Assuming you're not talking about falling on the floor and standing on it, and all those other odd things that can happen. But the population is very limited to 6. But if we go to this and say that, or you'll find I like 2-inch wood screws. What's the population for 2-inch wood screws? It's essentially infinite. We can't get at it. And so population is absolutely everything that we may come across. We can't get at the whole population, or very rarely can we get at the whole population. And so we're going to investigate samples. That's where sampling theory comes in. Sampling theory is part of statistics, it's part of uncertainty. How many measurements do we have to take before we've got good confidence in the data that we're measuring? That's the sort of thing we'd make things know. Yeah. In the Cal lab, you've got a set number. You use Cal blocks for calculus work? Yes. So I forget how many it is now. There's a set sequence of this number and this one and this one. And when you add them, someone somewhere sat down and said, how many do I need to do before I've got confidence that your measurement is accurate enough? So that's an example of, you don't get to control that, because it's set down, doesn't it? You must do this number of measurements. But someone somewhere has been looking at that and saying, that's how many you have to do. We'll talk about some of those kinds of issues as we go through. This one's difficult. The sample must be representative of the whole population. What does that mean? Population is everything. Sample is the bits we get to measure. Imagine your job is to go to the local grocery store and test out how long the milk is going to last after you've bought it. Well, you're not going to go and take the entire stack of milk from the store, well, unless you've got a big budget. You've got to go and sample a couple of containers. Yeah? So how do you make sure that your sample is representative of everything that's in the store?
It's a random.
Mm-hmm.
Yeah, it's a random sample.
So how do we pick on random? How do we know that the random is actually representative?
Well, first you collect all of them
But we can't get it all of them.
from a store. If you went to a
Your grocery store doesn't like you doing that. You're not allowed to go through the 12 and underlying to do that. Yeah, if you could get at the whole lot, it would be nice.
yeah.
The reason things I came across here are things like maybe the front, if the store is being looked after properly, the front will have the older milk and the newer will be at the back. If it's like my grocery store, they stack it up from the front and the old stuff's at the back and the new's at the front, the other way around. Or maybe it's just that the bottom one is always kept full because it's the little lady that stocks it. She can't reach the top shelf. Okay. If we're going into the local hardware store and going back to my 2-inch screws, and I don't know about your place here, but we have sort of racks of these are the 2-inch screws of this kind, here's the 2.5-inch screws. And now, maybe the ones at the top were made by one manufacturer or 1 week, and then the next one's down with the next week, and they're not rotating the stock. So yeah, we need a random sample, but picking that random sample can be extremely difficult. You can be very biased in the way you accidentally, if you just trust your own way. If you go and say, I'll take one from there, one from there, one from there, one from there, that's not random. You're just saying I'm going to take them corners. So it's very, very difficult here. And if you think of things like electioneer polling, that's a classic example of how do they know, you've seen it where they say, and so-and-so is leading, and the margin of error is plus or minus 4%. Yes? Seen those? What does that mean? First of all, they've had a hard time doing this, because they never get mine. You're doing a poll? Hang up. And they walk up to you with the clipboard, and I go, excuse me, around. But some people love to answer polls, so they go flocking up to them. They're not representative. But where does that plus or minus 4% come from? We'll learn out in statistics where it comes from. Okay, we're going to be looking, we'll be able to put a confidence, a percentage like that around our numbers, like it depends. So that's one of the things we're going to be looking at. So yes, the randomness, we're going to try and somehow get random, and typically we want to plan the randomness before we've actually seen the product we're going to be getting. If I said, here's a production line of pens, I'm going to take every 10th one. Is that random? No. What if somewhere down the line there's a machine that's got a carousel of 10 on it, and every 10th one is always a little bit shorter, always a little bit long? you would never find that you'd actually, you know how it goes. And so that's not random. So it's very tricky. You plan it before you actually start doing this stuff. Other bits and pieces on there. So let's read through this one. What does the first bullet mean? Estimating the characteristics of a given amount of data means, hang on, let me try and do this here. I'm trying to fit in with that. Investigating the characteristics of a given amount of data, fancy phrase for sample. Investigating the characteristics, statistics, things like mean, standard deviation, skewness, we'll talk about those soon. Investigating, calculate, requires dividing it into manageable groups. We'll see how we go into sorting for bins like histograms and things like that, because very often we don't want to deal with all of the data that's spooling in. We need to somehow group it, and then we'll work in those smaller groups. And you'll see the difference between having access to all of the data and if it's being grouped. Now, one of the reasons I'm talking about putting things into bins, like all the tens that are between this much and that much plus 1,000, that kind of thing, is that if you're in charge of measuring your own data, you can get access to every piece of information you measured. You say to Steve, go measure my pens and give me every single measurement that you took. I've now got access to all that data. But it's very, very common for us not to have access to that. Someone has already done a little bit of processing and put it into little groups or bins, and then so we'll see the difference between how to deal with lots of data and if it's been reduced down to a smaller set of data as well. We get slightly different answers. So we're going to be talking about finite or infinite amounts of data, or really we're looking at discrete and continuous. Here's where we look at finite and infinite. Whole numbers between 0 and 1. How many whole numbers are there between 0 and 1? You got it. That's the first quiz of the day. Answer 0. Between. Yes. And that becomes important to us very soon, the difference between or including, up to and including, and things like that. We'll talk about that when we look at grouping data. But really, it's getting at, it's really saying including 0 and 1 here. You're absolutely right, Russ. That was the trick question, and you solved it. Whereas, what about decimal numbers? As in 0.1, 0.2. How many of those are there between 0 and 1? Well, it depends how many points after how many. Yeah, exactly. So it's infinite at that stage. Comparable, we're going to be looking at discrete or continuous variables. A variable is the thing we measured. We're going to be using the word variable. It's a dictionary. It's a definition word, and the variable just means the thing we are measuring. If you're measuring the length of my 2-inch screws, the length of the 2-inch screws is the variable. If you're measuring, I don't know, the weight of students in class, I'm an outlier. Oh, maybe Russ is with me as well. We'll be outliers together. If you're measuring the weight of students in class, then the weight of the students in class is the variable. And so it's just a word that we use so that we don't have to keep on saying, and the temperature that we are measuring is, which say the variable. It's a great way of hiding what you're doing if you're talking to when you're talking to the bus. It's measuring the variable. And if they haven't realized you're measuring temperature or pressure or whatever, you can have a whole conversation and they haven't a clue what you're talking about because you're hiding behind the statistical definitions of the words. So we'll come on to what you can do about that if that happens to you. We have discrete and continuous. What do you think I mean by a continuous variable? What I'd like you to think about is a set of stairs coming up from, say, a parking lot to a building, and right next to it, a handicap ramp for wheelchairs. Yeah. The steps are discrete. If you're walking up the steps, you can only be at those levels as you go up. So we call that a discrete variable. It can only have set values. Whereas the handicap ramp going up, you can be at any height, depending on where you are up that ramp. That's now a continuous variable. You continuously variables varies from nothing upwards, as opposed to the discrete where we step up and go through. We're going to be treating them slightly differently. We actually will focus, you'll see how we just eventually ignore it, but I've got a question for you then. Is temperature in this room, temperature in an internal combustion engine, is that a discrete or continuous variable?
Depends on how you measure it. Depends on the resolution of the measuring device.
So you're coming into the answer there. Let me back off and ask the question again. Is the temperature, the actual temperature, discrete or continuous?
Discrete.
It is continuous, yes. If we have this temp, by the way, that's another of my rules here. You're not allowed to touch the thermostat on the wall. Okay. If I see eyes start to go down, I correlate the temperature that I set with how low the eyes are. So if by Thursday afternoon you're coming in with big, thick jackets on, it's because I thought, down it goes, down it goes, down it goes. So the actual temperature, if I was to raise the temperature, allow the temperature to raise, the actual temperature is going to increase continuously. So therefore, a continuous variable. But as Steve just said, once we have measured it, it will now become a discrete variable. In that case, whole numbers, because it only shows the whole degrees. Using a K-type thermocouple, maybe get to 1/10 of a degree, I think centigrade, something like that. Certainly no more than that. But now we've got steps. We're using something else. You're smiling, Daniel. Do you disagree with 1/10 of a degree for K-type thermocouple? You're going, what's a K-type thermocouple?
Been a while.
Been a while, okay. They're the ones with the yellow wires with the little red tracer on them. The cheap ones. Everybody uses.
That's true.
Here's a clue. If you don't know anything about thermocouples, but you want to sound real clever, you go up to a system, oh, how are you measuring it? Oh, I'm using this. Oh, it's a thermocouple. Yeah, yeah. So you just say, oh, it looks like a K-type thermocouple. The 99% chance you're right. And they go, ooh, he's clever. But in that case, probably about 0.1 of a degree. But you use the word resolution. You don't explain that to people.
It's the amount that you can see, like past, we'll say, the point. So the whole number. So it would be like a resolution of 0.00 gives you.
Yes, exactly. Look at this rule here. Assuming I can only measure at the individual tick marks, then the resolution of this is 2 or 1/8 of an inch. 16 centimeters. So the resolution is a 16th of an inch. We cannot resolve any more. If the measurement varies by less than a 16th of an inch, I can't use that to measure. So at that stage, if I'm now measuring, let's say I needed to measure the size of this here, I go, oh, yeah, 2 to the 16th. Oh, 2. Ooh, 2. The resolution has converted this continuous variable, the length, into a discrete. So most of the time, do I hear a fog horn?
It sounded that way.
Because I can see it again. Okay, I've got nightmare flashbacks now. Smallest unit of measure, that's kind of. We can get below that actually. We're going to do an experiment later on this week where I'm going to get you to, because the rule only has a 1 centimeter resolution, but we can actually measure more accurately than a centimeter without guessing. Try and think that one through. Yeah, there you go. That's obvious. But it isn't right now, is it? Oh, it is. So we're going to be dividing large amounts of data into classes or bins or groups, different names by different people. You hear them called groups, bins, classes, whatever you want to call them. It doesn't really matter too much. And we're going to see how we're going to look at breaking stuff up. We're going to be talking about having classes of equal width. That is not critical to the analysis, but it really helps. And you often find that if you look in the newspapers, if you look at these little histograms, for example, very often if you look at the axes, if they put axes on there, you know, you've got a bar that's this big and a bar that's this big. Okay, depending on whether it's MSNBC or Fox News, this is either the Republicans and the Democrats or vice versa, depending on what they're looking at. How much we hate people or how much we love them, depending on, it doesn't really matter. And then you look at the axes and you find that actually they're great big things and they're really the same height, but they're just taken off the top. You ever seen graphs like that with the expanded scales? Or we can change the width of the bins and all of a sudden what looked common sense before all of a sudden becomes almost impossible to interpret, and you can cheat. Modify the story that you're telling people. Let's get into some of the ideas here. Here's a stack of numbers. Don't care what it is. We've got 40 packets of something. We're measuring the number of components in it. It's an artificial one. Of course it is. It's done to make it fairly straightforward. Without looking at that, just look at this up. Tell me what you can tell. Tell me. What can you see from just this set of numbers here?
Runs a range from 3 to 10.
Yeah, it looks, you have to kind of scan the whole lot, but it looks like it goes from 3 to 10. So it's not under 3, not more than 10. 4s and 5s, and there's a lot of 3s cropping up, but it's not easy to really see. This is all the information. Everything we need to know probably is in that information, but it's not easy to interpret. So the analysis, I'll find out what it is. The analysis now is, the first step in this case is to put them into bins. And the bins that I've chosen here are discrete values. If this is number of components in a packet, then we're hoping we only get whole numbers. So there we go. Oh, now what can we store? I meant to point over here, sorry, because Mark's recording this, and you can't see if I wave up here. You can see if I do this. So what can I see now? I've used the 5-bar gate type of approach here. You've done that sort of thing before, haven't you? Probably middle school. And basically we're just mark off. And now I know that I had 6 3s, 10. Oh, look, there's a lot more 4s and 5s, and only a couple of 9s or 10s floating around. Yeah, we can see that much more easily than going back. Now, okay, it's only 40 numbers. What if there's 4,000 numbers? That's not so easy to see, is it now? But if you have 4,000 numbers and did the same gay thing here, we would be able to see. Now, does this have the same information? It's lost some information. Going from here to here, you've given up some information. It's very common in the analysis, the statistical analysis, for us to lose or throw away information. We have to make sure what we throw away isn't important.
The order of
Exactly. Good for you, Rob. Exactly right. The order. Here we know how many. Oops. Here we know how many, but we don't know the order. So if we were looking at this, an order was important. The first box off the line had 4 in it. The next had 6. Ooh. Is this slowly increasing with time and we're giving more and more power as we go through time, or is it decreasing, or we've lost all that information about order? It's very common in statistical analysis that we're giving up information. So remember, we may be finding numbers that we can spout around and use, but you have always given up something the more analysis you do. It's up to you to make sure that information you've given up isn't the critical thing that's needed for whatever it is that you're doing. So there's a graph on the left. Bar chart, histogram, line chart, whatever you want to call it. Across the bottom, how many packets of the size, the number in each group. And now that is exactly the same information as, oops, went back too many. It's exactly the same information as here. But now we're seeing it graphically. Which one's easier to see? The graph. We like pictures, don't we? Engineers like pictures. What about the graph on the right? Pie chart. Have any of you in engineering, for engineering numbers, not budgets and things like that, but for engineering numbers, have any of you ever found a use for a pie chart? I haven't.
Yeah, if it's financial analysis and things like that, that can be nice. But I've never found a use for engineering stuff to have it. I'm sure there will be one somewhere. Guess what? Nobody's been on these courses has ever found a use for one yet either. So maybe we can say we don't use them. I would have to say that. So what about a continuous distribution then? So I've got a continuous distribution. I've got 20 volts. They're measured in centimeters. Doesn't matter whether it's diameters or lengths that we're looking at. Probably lengths. And so I've got a continuous variable, which is the length of the volts. What can you tell from the raw information that's been measured up here? It's a little more tricky to see this time, isn't it?
Standard deviation is really large.
Maybe. That's a subjective thing, though, isn't it?
Until you do
It may be good.
Yeah.
Yeah. You see where I'm coming from now?
Yeah.
There's a big spread. Just say it's a big spread. More difficult to see. I lied to you. Kind of. The length of the bolts is a continuous variable. Well, what have I shown here? Discrete. It's 2 decimal places. So already we're finding that continuous variables are nice for mathematicians to analyze, especially if you've got functions to play with things. But in the real world, we're pretty much always going to be working with discrete. Now, if the resolution of my measurement device was sufficient that I could get down to 5 or 6 significant figures, assuming that it meant anything for this bit of bent up, beaten up machine metal, then the difference between discrete and continuous is nothing, really, in practice. But here we really have a discrete one. So we can see that the largest is 6.7, the smallest is 3.8, the range is about 3 centimeters. And so what I'm going to do is I'm going to divide this lot into groups. And what I'm going to do is I'm going to say I'm going to take 6 groups, 6 bins, 6 classes. All mean the same thing. Why did I pick 6? Why didn't I say I'm going to divide it into 2 bins? Or 10 bins? Or 20 bins? Or 100? Why did I pick 6? What we'll find is if I just gave you a dump of data and said, here's a whole stack of data, put it into bins on a histogram. If you use somewhere between 5 and 15, that is and again, those 5 to 15 should be 3 to 18 or 6 to 12. But that kind of number of bins for most kinds of data will give you a graph which is probably representative of the data. It's a rule of thumb. There are lots of statistical equations you can dive into, doing some high-end math, and what do? They kick out a number which is between 6 and 50. And in the end, it doesn't make a lot of difference. There's nothing to stop you dropping down to 2 bins. So I can say everything that's bigger than 5 go in one, everything that's smaller than 5 go in the other. Yeah? It's like a yes-no. Is it big enough or not? And if we're only interested in is it big enough or not, that might be a good solution. The most number of bins I've used for a real set of data was 300. I remember that number well. It was analysis of student exam performance, and the raw score was out of 300, and we had like 800 students take the test. And so I split this lot out with a bin size of 1 for everything there, and then looked at the distribution of the data to try and sort out grades, etc. That was a proper analysis for cutoff. But if you go somewhere around about this 6-ish kind of number, then it's okay. And so what I'm going to do is I'm going to pick the smallest number is 3.8. So in this case, I'm going to pick the lowest bin break to be at 3.75. And the upper 6, the biggest number is 6.7, so we need to sort of spread out. We want to have these bins to be a comfortable gap. Here we don't really want them to be every 0.37 of a centimeter. Yeah, you can do that, but doesn't it make sense in engineering to make them whole numbers, quarters, halves, and or something which is more of a natural kind of size? So in this particular case, what I've done is I've taken these groups here, and the class is 3.75 to 4.25, and then every half an inch based on that, half a centimeter based on that, up to the top. So now, 5-bar gate, there's the frequency, and there it is plotted out as you go there. Now, I want you to notice that here to here, I've assumed something. I've assumed that I can't have a 4.245. How can I not have a 4.245 in this particular example?
You don't see that resolution?
Yeah, because we only measured the 2 decimal places. There's going to be a lot of times where we need to be very, very careful to make sure that we are doing that, and we'll see in a moment how we do that. So in this case, really, although we say it's the height of these bars, which is a measure of frequency, really the area becomes a critical quantity. But since all the bins are equal width, then the height, the visual height, is a thing of importance. So we're going to have to remember, really it's area. We'll see an example come up where area now it suddenly changes the pattern. But if we have equal width, then the height is now representative of the number in each region. So there's the height. So let's have a look if we had taken the same set of data, but this time I have changed the grouping so that I've combined the first two groups, and I got a 3.75 to 4.75. I've now kept this one the same. I've combined these two groups, and I've left that one the same. Going back, how do you think that's going to change that graph?
You can even it out.
Let's see. The same data. So, are we saying that we get most at the low level and hardly any at the top? Or, going back a couple, are we saying it rises and then goes down? Which is the true story? And yet that graph and that one have just come from the same set of data.
So the old theory that statistics, you can make statistics tell any story you want to tell.
Yeah. Yeah, exactly.
Manipulate it.
Exactly. So, fingers in the air, please, Aaron. You need to tell your boss that as the size gets bigger, we have fewer and fewer and fewer. Then you show him this graph. You want to show him it's focused around a certain peak, you show him the previous graph. Now, since Aaron's now been on his course, he knows that area is more important. Your eyes don't focus on area. Your brain focuses on lengths rather than areas. If I show you something, two spots, and I say one is twice the size of the other in terms of area, your mind would have given me about 25% increase. If I put two circles on the screen and said, the one is twice the size of the other, your mind, if I just said, what's the ratios, you'd come up with about probably 25%. Your mind doesn't see area. It sees lengths. So no, we're not lying. That sure as heck looks like it, doesn't it? So to me, it's very important with statistics. You don't finagle the numbers to tell the story the boss wants to hear or the one you want to present. You try and spend some time making sure that the numbers you present are truly representative of what's going on. Okay. I just feel that's the truth. That's the truth. Okay. There's something wrong with this graph now, but let me tell you what we tried to do here. We're taking that first graph, not labeled, but this is the length in centimeters and the frequency, the number that we got. And now I've put little X's at the midpoints of the graphs. Because if we've just got a few bars, then it's okay to put a bar chart like that. Well, what if you've got a couple hundred? Well, that's getting so cluttered up with ink and lines and things you can't see anything. So it's very common for us to go to the center points and then join the dots. But there is now something very, very wrong with this graph. Imagine that I had presented you just the blue line, maybe with the black X's, maybe not, and I hadn't given you any of the red bars. I'm presenting you wrong information now. What I'm showing you is this curve is smooth. If I see a smooth line like that, that's telling me, as an engineer, that I know information all the way along that line. Really, I should just be showing you the X's, and if I want to do it visually, I should be drawing with straight lines.
Yeah, the plots were the only thing that matters.
Right. I don't know anything that's going on here, but if I took that value from the blue line at this point, then it would be telling me something. Similarly here, if I took this point, it's trying to tell me something from that line because it's smooth and continuous. So if you're joining dots, join it with straight lines if you have to join the dots. Don't put a smooth function through. Okay. I think that's very important. So we're taking the midpoints and then join the dots between. So now we've got a line which is, our eyes are much easier. It's even easier for us to see. And the area under the curve is always going to be something really important to us. As we dive into this stuff here, we're going to find the area under the graph is important. If we find the area under the graph, it's going to give us something really, really useful. Now, there's another thing we can look at. What we've looked at here essentially is a frequency distribution. How often does something happen? But another one that we use a lot of the time is called a cumulative plot. And a cumulative plot, if I come to this point here, for example, we're halfway through, this point here, and my question is, how many are that size or smaller? The answer is 9. How many are this size or smaller? The answer is 19. Now this graph will always start at 0 down here. It has to, because if you go back to how many bolts are less than 0 inches long, the answer is 0. So it's got to start at 0. And we'll find with all of the graphs we do for all the statistics, they'll start at 0. There's cumulative plots. They always rise. It's called monotonically, which means they always keep going up. There's never any little dips. They have to keep going up because you're adding up and adding and adding and adding, never take away. And then they always at the top, depending on the scaling that we use, at the top, they'll either come to the number of samples, there were 20 samples, or if we're looking at a probability function, it'll always go to 1. We'll see that come up as in 100%. Notice that because this line is smooth rather than straight lines, oh look, apparently if I come to this number, there are just over 20. Well, that's nonsense, because there are only 20 samples measured. Another example of why we shouldn't use straight lines. So this is called the cumulative frequency or cumulative probability when we get on the probability function. And we saw that come up. So let's take a 5-minute break, maybe 10 if you need it, and then we'll come on to our central tendency. My question when you come back is going to be, what does central tendency mean? We're going to ask you to write that down, what you think central tendency is.